Have you ever really stopped and wondered what the universe is truly made of? I mean, not just atoms and molecules, but what are the absolute most fundamental ingredients? Well, we're going to dive right into that because the answer, it turns out, is both way simpler and a whole lot weirder than you could ever imagine. So, we're going to peel back the layers of reality. We're going past the cells, past the atoms, all the way down to the very blueprint of existence itself. We're on a mission to answer this one gigantic question. All right, so first things first, let's take a look at the ingredients list for the entire cosmos. Now, you'd think it would be this enormous, complicated recipe book, right? But it's actually surprisingly short. Yep, you heard that right. The incredible diversity of everything in the universe, from a giant exploding star to the chair you're sitting on, all of it boils down to just two basic families of particles. It's really the ultimate case of cosmic minimalism. And here they are, the stars of our show, quarks and leptons. These are the true, rock-bottom, fundamental building blocks of matter. Now, you've definitely heard of the most famous lepton, the electron, that tiny particle zipping around in every single atom. Quarks are a little more shy, kind of hiding out in the very heart of atoms. And check this out, this is how it works. Quarks are super social. They never hang out alone, they're always in little groups. And to build the stuff that you and I are made of, you really only need two flavors, the up quark and the down quark. It's like a recipe. Combine two ups and a down, and boom, you get a proton. Combine one up and two downs, and you get a neutron. And with protons, neutrons, and electrons, you can build every single atom on the periodic table. Simple as that. So, when you put all of these particles together, the quarks, the leptons, and a few others we'll touch on, they form this incredibly elegant chart called the Standard Model of Particle Physics. Just think of it as the ultimate periodic table. This is the complete cast of characters for the story of our universe. Okay, so we've got the ingredients, but what about the recipe book? How do these particles actually interact with each other to create, well, everything? Turns out there are just four fundamental rule sets, or forces, that run the entire show. You've got the strong force, which is like super glue holding the nucleus of an atom together. Then there's the electromagnetic force that governs all things light and magnetism. The weak force is a bit more obscure, but it's responsible for certain types of radioactive decay. And of course, good old gravity, the force that holds planets, stars, and entire galaxies together. But here's where it gets really weird. A force isn't just some invisible, spooky action at a distance. In the quantum world, forces are communicated by literally exchanging messenger particles. And these little messengers are called bosons. For example, the photon carries the electromagnetic force. Gluons carry the strong force. Yeah, they literally glue quarks together. And the W and Z bosons carry the weak force. So basically, every interaction in the entire universe is just a constant game of catch with these force-carrying bosons. Okay, so now we have our particles and our forces. But this perfect blueprint has a dark secret, a kind of mirror image that leads to one of the biggest, most profound mysteries in all of science. And that secret is called antimatter. The idea is, for every single particle of matter, there's an antiparticle. It's a perfect twin in almost every way. Same mass, same everything, but it has the exact opposite electrical charge. Take a look. The electron we all know and love has a charge of -1. Its antiparticle, called the positron, has a charge of +1. A proton is positive, an antiproton is negative. It's a perfect mirror image. But here is the crucial rule. These twins cannot coexist. If a particle of matter ever meets its antimatter counterpart, they instantly annihilate each other. Poof! They vanish in a flash of pure energy, a total conversion of mass into light. And this leads us right to the heart of the mystery. Our best theories tell us that the Big Bang should have produced matter and antimatter in perfectly equal amounts. But if that's true, they all should have found each other and canceled out, leaving behind a universe filled with nothing but light. So why are we here? Why is there anything? Just try to imagine the early universe. In those first fiery moments, it was this thick, chaotic soup of particles and antiparticles constantly being created and destroyed. They should have all canceled out, leaving absolutely nothing behind. But they didn't. Something survived. Now, our leading clue to this cosmic puzzle is a tiny imperfection in the laws of physics called CP violation. It suggests the mirror between matter and antimatter isn't quite perfect. For some reason we still don't fully understand, the rules were slightly biased, allowing just about one extra particle of matter to survive for every billion pairs that were annihilated.
That tiny imbalance, that's the only reason we exist. So how in the world do we even begin to investigate it? How do we test these incredible mind-bending ideas?
Well, we can't exactly build a time machine and go back to the Big Bang, so we do the next best thing. We build these absolutely enormous machines called particle accelerators to recreate the energy and conditions of those first few moments right here on Earth.
The biggest and baddest of them all is the Large Hadron Collider, the LHC at CERN. This thing is just mind-boggling. It's a massive 27-kilometer ring buried deep underground. Its whole job is to accelerate protons to 99.9999999% of the speed of light and then just smash them into each other, creating these tiny fireballs that mimic the Big Bang.
So how does a beast like this even work? Well, this gives you the basic idea. You get some particles moving, and then you use thousands of incredibly powerful magnets to bend their path into a circle. They get a little energy boost with each lap, going faster and faster and faster, until they're ready for the big collision. Now, these experiments can create tiny amounts of antimatter, but it is incredibly difficult and outrageously expensive. To put it in perspective, scientists at CERN actually calculated that creating just a single gram of the stuff would cost about $62.5 trillion. That makes it, by far, the most valuable substance on Earth. So just think about that. Our entire universe, every star, every planet, you and me, we're just the leftovers. We are the rounding error from a cosmic battle between matter and antimatter. We are the survivors of a perfect cancellation that wasn't quite perfect. And the quest to understand why that tiny imbalance happened, well, that's not just particle physics. That's the quest to understand why anything exists at all.